Okay, in this video, we're going to be looking at the conservation of energy worksheet. And we're going to start off with right away with the law of conservation of energy. So remember, I will call this loco E. And what law of conservation of energy states is that the total amount of energy in any process must remain constant. So I'll write that out. Total amount of energy in any process remains constant. Now you will see me write this when there's no friction and the energy transfer is just between potential and kinetic and back and forth. You'll see me write this as sigma, hang on, make that a little cleaner, sigma E initial, so that's the sum of all initial energies, must be equal to the sum of all final energies as well. And again, if there's no friction or anything like that, and just transfers back and forth between potential energy, so you can say PE initial plus KE initial must equal PE final plus KE final. Now, if there's losses to work and energy, and I'll put this in here, if for some reason we're going to lose work to friction or heat or something like that, then I like to put a little plus whiffer. So that's work lost to friction or other places or something like that. You'll sometimes see it in terms of the reference table, and I'll erase this for right now. The other way you'll see it is you'll see it as plus Q, where Q is any energy that is lost to any other process. Okay, so if we look at number 2, it tells us we've got a 200 kilogram boulder 1,000 meters above the ground. What's the potential energy? So straightforward from the last time. So PE. And actually, I should guess this. So we've got a mass of 200 kilograms. I've got a height of 1,000 meters. And since it's above the ground, we're talking about the acceleration due to gravity as well. So 9.81 meters per second squared. And then the potential energy is just equal to mgh. So I'll write that in 200 kilograms times the 9.81 meters per second squared. And then times the 1,000 meters, which seems excessively high, but that's okay, 1,000 meters above the ground. Okay, and when we calculate that out through, and I'm going to put it in scientific notation, that's 1.962 times 10 to the 6th joules, or 1,962,000 joules. Now, what's kinetic energy when it's 1,000 meters above the ground? It doesn't say that it's moving, so we can say that its kinetic energy is going to be 0 joules, and that's because it doesn't have any velocity at that point in time. If it had a velocity, then we could find it by using 1/2 mv squared. Now, the boulder begins to fall. What is its potential energy when it's 500 meters above the ground, and where did that lost potential energy go? So we're going to use this, our sigma E initial equals sigma E final, to help us answer the second question. So the potential energy initial plus the kinetic energy initial must equal the potential energy final plus the kinetic energy final. Okay, so we're going to use this to answer the second question, but let's go find out what that potential energy is when it's above the ground. So we have the same mass as before. So potential energy to gravity is still that 200 kilograms. Oops, let me put in the equation. Don't get lazy here. mgh. So we have our 200 kilograms as before. We still have our 9.81 as our g, meters per second squared, but now the height is only 500 meters, so 500 meters. And when we calculate that out, we're going to get 9.81 times 10 to the 5th joules. Okay, so if we can put this back in, again, using our law of conservation of energy, I'll go back to orange. 1.962 times 10 to the 6th joules is our initial potential energy, plus 0. Joules is our initial kinetic, and that's 9.81 times 10 to the 5th joules. And since those two aren't equal, we know that that lost potential energy, that quote-unquote lost potential energy, had to go into kinetic. And we can find out how much kinetic energy by just subtracting this. And so 1.962 times 10 to the 6th minus 9.81 times 10 to the 5th. And so our kinetic energy final, or at 500 meters above the ground, so I can put the kinetic energy final at 500, just to remind me it's not really final, it's at the 500 point, is just 9.81 times 10 to the 5th joules. And yes, that should be a 5, not a 6, my fault. Now this is just because it's breached the halfway point, so it's lost half of its potential energy, and because we're ignoring friction, that half went into kinetic. So they're going to be at the halfway point, the potential is going to have to equal to the kinetic. Now, part E, what's kinetic energy of the boulder just before it hits the ground? We're going to do the exact same thing, except I'm going to go down here. All of this stays the same. The initial stays the same. So 1.962 times 10 to the 6 joules plus 0 joules is our kinetic energy. But now, when it hits the ground, its height above the ground, so PE final is mgh, but now its height above the ground is going to be 0. So 200 kilograms times the 9.81 meters per second squared times 0 meters, that gives us 0 joules for our potential energy. So we can change this to 0 joules plus the kinetic final. And so now we can find out that our kinetic energy final is going to equal 1.962 times 10 to the 6th joules. So in this case, all of the potential energy we had at the top now becomes kinetic when it gets to the bottom. We look at the bottom, the next one, number 3, says a roller coaster shown as designed below. Roller coaster starts at the top of the first hill from rest. So right here we have initial velocity of 0, which means then our kinetic energy initial is also going to be 0 joules because it's 1/2 mv squared. So as it goes down, as it starts to go down, it's going to lose potential energy. Now the potential energy at that point is equal to mgh. But as it goes down, it loses potential energy. So PE will decrease. And in the process, the kinetic energy will increase. Until we get down to the bottom, at this point in time, the potential energy here is 0 joules. And our kinetic energy will be whatever the potential energy was initially. As it goes back up, and I'm going to put this in a different color, as it goes back up, our potential energy is going to increase. And that because of that, because we're raising up our height, and our kinetic energy will have to decrease because it's going to have to slow down. Now, because of the law of conservation of energy, the total amount of energy is going to equal that PE. So it's going to be at the exact same height that it was before. So this thing will never, ever get to that top of that second hill. So how can we fix this problem? Well, one of two ways. One, we could lower that second hill. Lower second hill. And in the process, then, the height won't be as much, and it will now have enough energy to get up to the top there. This is why most roller coasters you ride, the second, the third, the fourth hill are always smaller than the previous one. Or the second thing we could possibly do is to give it some initial kinetic energy. And that initial kinetic energy will help it to have enough energy to climb up over the hill. And so as long as that potential energy right there, the height, is greater than that, we're good. Sorry about that. I'll continue again. We could give it initial velocity at the top of the first hill. And so then it would have enough kinetic energy as long as it gets up to the top. Okay, moving on to number 4. Use a slingshot to fire a rocket, stretch the rubber band back, storing potential energy. So this is going to be elastic potential energy. Elastic potential energy. Remember, elastic potential energy, PE, stored in the spring, is equal to 1/2 k x squared. So that's how much energy is going to be stored in the spring. So what it does tell us that it's actually 100 joules. So we don't actually have to go find it, which is kind of nice. So this potential energy stored in the spring initial. So PE initial is going to be 100 joules. Now, when we release that, so we pull it back, it's got that 100 joules stored in it. When we release it, that rubber band snaps back, in which case then our potential energy final is going to end up going to 0 joules. So if we use the law of conservation of energy, so loco E, so sigma EI, oops, too many bands there, has to equal a sigma EF, and so the potential energy initial plus the kinetic energy initial equals potential energy final plus the kinetic energy final. And so I can say that I had initially, and I'll put this in a different color now, 100 joules of potential energy, and I had 0 joules of kinetic energy. And the reason for that is when I pull that back, that rock initially has no velocity, so it's not going to have any kinetic energy either. Then when we release it, that potential energy final will go to 0 joules, and so we're looking for the kinetic energy it has when it releases. So as we know, the kinetic energy final is going to end up being 100 joules. Now, how much energy will it have if it loses 10 joules to heat and sound? So this is that modified kinetic or loco E that I was talking about before. I'm going to slide this over just so we can see it. We still have our potential energy initial plus kinetic energy initial is equal to potential energy final plus kinetic energy final. But now we know that this initially is 100 joules for potential energy. The kinetic energy is still 0 joules because it's not moving. When it releases, potential energy final now becomes 0 joules, and it tells us that the kinetic energy final, let me change this, is going to be 90 joules. Now, so you have 100 is equal to 90. We know that that's not true. So what this means is we lost some energy due to friction. So I'm going to put it as a plus Q. I go back and I say, okay, plus Q, plus Q, plus Q. That Q is the energy that is lost to heat, light, sound, friction, something like that. And I can solve for the Q, and that's going to equal 10 joules. And now looking back over part B, I realized that I solved that completely backwards. I had it wrong in my head. But if you go back, you can tell I went to the 90 instead of the 10. So it said that it lost 10. So now the kinetic energy, I'll put the actual right answer here. The kinetic energy it's going to have is being 90 joules. So I solved that ahead of time. All right, so number 5, it says the pendulum has 15 joules potential energy at the top of its swing. Now, I always like to draw this out. And again, I encourage everybody, draw a picture, draw a picture. So here's my pendulum. It's going to swing on down through and then come back up, hopefully. And then we'll go from there. And then it's going to compute like that. So it's going to swing back and forth, back and forth. At this highest point, we know its potential energy, it tells us, is going to be 15 joules. And at its highest point, it stopped. So we know that the kinetic energy is going to end up equaling 0 joules. So as this thing goes down, as it continues to go down, it's going to lose potential energy. It loses PE, and the reason for that is because the height decreases. Remember, at the end of the day, potential energy is equal to mass times acceleration of gravity times the height. And so since the height is decreasing, the potential energy goes down. And so we assume that when it gets down to this lowest point, I'll put this in kind of a blue little spot here. When it gets to this lowest point, its height is now going to be 0. So h is going to equal 0 there. And since the h is equal to 0, at the bottom, the potential energy will equal 0 joules. So using our law of conservation of energy, that the PE initial plus the KE initial must equal the PE final plus the KE final. So I know that I have 15 joules up top in potential, 0 joules in kinetic. Potential energy final is going to be 0 joules plus my kinetic energy at the bottom. So this is KE final. So doing the math here, my kinetic energy at the bottom has to be 15 joules. Again, law of conservation of energy. Okay, at some other time, the pendulum has 8 joules of potential energy. So we're talking about somewhere like maybe right here. Maybe when that pendulum's now at this point right here, its potential energy is now 8 joules. Now, the thing that we started with stays the same. So we can take this part right here and bring it on down. The PE initial plus KE initial is 15 joules plus 0 joules. You're thinking, well, wait, isn't this a different situation? It's still the same pendulum. It still is going back and forth. So the initial that we had, the total amount of energy we had in the system is 15 joules. That's going to equal my potential energy final plus the kinetic energy final. Now I'm using final loosely here. Now I'm going to say that's that part at that spot that we just located. But now it says that my potential energy there is 8 joules. So I can solve for my kinetic energy final, at which point now 15 plus 0 is equal to 8 plus my kinetic energy final must be 7 joules. Now, for part C and pendulum B, what would the kinetic energy be if it loses 2 joules to heat? For that situation, we look back and we just rewrite our potential energy. So we still have the PE initial plus KE initial. That stays the same. That's our total amount of energy we start with. So 15 joules plus 0 joules. And now we've got potential energy final plus kinetic energy final. But now it tells us we've got our plus Q here because we're going to lose 2 joules to heat. So once again, it tells us that our potential energy, and I'll put this back in orange, potential energy is at 8 joules because we're back at point B. We're looking for the kinetic energy final, but we know that Q, and I'll put it back in that blue pencil, is 2 joules. So 15 plus 0 is equal to 8 plus KE plus 2. So now my kinetic energy final has to equal 5 joules. All right, and for our last one here, we've got a 1 kilogram ball 10 meters above a table when it's dropped, and it bounces to a height of 7 meters. They want to know how much energy is transferred to heat and sound during the bounce. So again, if you draw a picture, it's going to help. Initially, it's up here. It is 10 meters above the ground when we first drop it. And I'll make it a nice red ball there. And it's going to go down. I'll put this in orange. It's going to go down. It's going to bounce back up. But now when it gets up to this next spot, it only goes to a height, I'll put this in green, of 7 meters. Now, at both times, I know at this spot right here, its velocity is 0 because I'm dropping it. I know at this spot right here, its velocity is 0 because it's getting to its highest point, and that should be meters per second. So I can still use my law of conservation of energy. I can still say that PE initial plus KE initial is equal to PE final plus KE final. And then if there's going to be a plus Q in there. Okay, and I'll show you, actually, let's leave it off for right now. And then I'll show you how I'm going to put this in. So I need to find out, I already know, and I can scratch this out, I already know that my kinetic energy initial is going to be 0 and my kinetic energy final is going to be 0. So I need to find my potential energies. So let's wander over here and let's guess. So we've got a mass of 1 kilogram and we have a height of 10 meters. And again, because it is gravitational potential energy, we're talking about 9.81 meters per second squared here for our that. So our potential energy initial, PE initial, is going to equal mgh. So 1 kilogram times 9.81 meters per second squared times the 10 meters. So when I get that, I'm going to end up getting a grand total of 29. No, that can't be right. Hang on, let me double check my math here. Sorry about that. I looked at the answer key and said, oh, that can't be right, but I went and do the intermediate math. So when I do this, 1 times 9.8 times 10, that's just the potential energy initial is going to be 98.1 joules. So this potential energy initial, 98.1 joules. But now I need to find out my new potential energy. And now the only thing changes there is now my height, and I'll put this in blue. My mass is still 1 kilogram. My height is now 7 meters. And my G is still the 9.81 meters per second squared. So I can still find my potential energy, mgh. So I'm just going to jump to it, 1 kilogram times 9.81 meters per second squared times 7 meters. And so my potential energy now is going to be 68.67 joules. And again, if you rounded later, if you went 68.7, that's perfectly fine too. Okay, so when this comes back up, okay, so we've got that, that's going to have to equal 68.67 joules. Now we already know our kinetic energy initial and kinetic energy final are 0, but I look at this and I'll highlight it. This is not a true statement. Our potential energy initial is not equal to our potential energy final. So in order to make this work, I have to put in my plus Q, because that's going to be the energy that is lost in the process. And so to find out how much energy is lost to heat and sound, I just solve for Q. And so you get 98.1 is equal to 68.67. And when you subtract that, you get 29.43 joules. And that's what my answer key said before, which may be a little confused. Okay. Now, part B, explain why this ball cannot bounce to a height of 12 meters if it's dropped. Well, if we went and found the potential energy at 12 meters, and I'll just do this here, mgh. So I'm going to go the 1 kilogram times 9.81 meters per second squared times the height of 12 meters. So if I pop that in, I'm going to quick just do it right here. So 1 times 9.81 times 12, 9.81 times 12, I get 117. 117.72 joules. So I started off with 98. That was my initial, 98.1 joules. It now has come 117.72 joules. This is not possible. Okay, it's impossible. This number, and I'll circle this here, this number can never be bigger than my initial. It can't happen. So that means that my work lost to friction would have to be negative. So somehow friction, heat, and sound would have to go into it in order to make that happen. So there's not enough initial energy. Not enough initial energy. So if I wanted to remedy that, if I wanted to make it bounce up to that height of 12 meters, I would have to throw it down. I would have to give it extra energy at the beginning. And usually that's done by throwing the ball initially. Okay, and again, that is usually done by throwing the ball, because if you throw the ball, then it's going to have a velocity, and then it's going to have a kinetic energy. So you'd have a PE initial plus a KE initial, and that would have to equal our total energy afterwards. So we'd have to equal that 117.72 joules, and that's assuming we didn't lose any to heat and light and everything else. If we did, we'd have to put in even more. Okay, so I hope this helps, and hope we were mildly entertained from all the stuff going on. So have a great night. We'll see you later. Bye.